So now that we have a little bit of a handle on some of the rules and properties associated with calculating probabilities, let's work some examples. So the first example we'll look at is that of a discrete finite probability. And let's assume that we have a die that is four-sided. So there's four different sides to this die. It can have a result of 1, 2, 3, or 4 on each roll. And that we treat this kind of similar to how we did the coin flip earlier when we were talking about discrete probabilities, where we use some x-axis to define our first roll and some y-axis to define our second roll. Now you can see that there's a intersection for 1, 1, an intersection for I got a 4, then a 1, and all of these different regions, all of these event spaces are part of the possible outcomes in our sample space, omega. Now, to actually do things with this, to calculate probabilities, we have to decide what the probability of each of these individual events occurring is. And for simplicity, we're just going to assume that every outcome has the probability 1 over 16. There's 16 unique events here, and we're just going to assume that they are all equally likely. Now, you'll find in most cases that's not necessarily the correct assumption, but for simplicity, we're just going to make that assumption in this case. Now, let's find the probability that x is equal to 1. Remember, x is just our first roll. So basically what we're saying here is that we want to know the probability that that first roll came up as a 1. And so in a graphical form, this is super easy to look at. We can say that we got a 1, 1, we got a 1, 2, 1 and then a 3, and a 1 and then a 4. And so anywhere along this column, we've established that x is equal to 1. And so as you can see, there are 4 different possible outcomes whereby x is equal to 1. Now, as we've said, each outcome has a probability of 1 over 16. So the probability of x being equal to 1 is simply equal to the number of outcomes where that can occur multiplied by the probability of each of those outcomes, which is 1 over 16, which is just equal to 1/4. As you can see, this isn't all that complicated. So let's look at a slightly more complicated example. Let's say that we want to find the probability that z is equal to 4, where z is the minimum of x and y. So basically we're saying that the lowest value is 4. Well, there's only one possible situation where the lowest value of x and y is equal to 4, and that's just 4, 4. So in this case, we know that there's only one outcome. The outcome has the probability 1 over 16. So the probability here is just equal to 1/16. Now in our final case, let's take the probability that z is equal to 2. Now remember, z is just the minimum of x and y. So we're going to calculate now what the probability is that the minimum of x and y is equal to the number 2. So in that case, I can pretty easily say that 2, 2 is a valid option. I can also say that anything along this column where y is not less than 2 is a valid option as well, is a valid outcome. So in that case, we're looking at the intersection of 2 and then a 3, and then a 2 and then a 4. And then the same thing applies for this row. Anything where y is not less than 2 is a valid outcome. So that's going to be this intersection of a 3 followed by a 2, and then of a 4 followed by a 2. And you can spend more time and look at this if you need to, but those are the only 5 possible outcomes where z is equal to 2. So again, just using the counting that we've been doing, assuming that every probability has, or that every outcome has an equal probability, we can simply say that this probability here that z is equal to 2 is just equal to the number 5 times 1/16. Or in other words, it's just 5/16. And as you can tell from this example, one of the things that is going to be pretty common amongst probabilities is this concept of counting. And so we will actually be spending a chunk of this section later of this lecture just discussing some simple rules for counting. And so again, being able to count is kind of important in probability. Now, the next thing that we'll talk about that follows directly from that example is this thing called the discrete uniform law. And it basically says that if omega, our sample space, consists of n equally likely elements and A consists of k elements, so before we dig too much further in that, let's actually draw out what this looks. We're going to have an element map here, all of these different elements, and we're going to say that there are n equally likely elements. In this case, I've drawn 9 elements, and each of those are equally likely, so the probability is equal to just 1/9. And we have some event A that consists of k elements, so k in this case being equal to 4, then I can simply say that the probability of event A is just equal to k times 1 over n, 1 over that number of elements. And this is basically the same formula we used on the previous slide. We've just now generalized it into a form that you can use for future assignments. So this is, again, the discrete uniform law, which basically says that if all elements are equally likely outcomes, then I can just multiply the number of elements within that event by the probability, which is just 1 over the total number of elements. So this section wouldn't be complete without looking at a continuous probability example. And so the uniform probability law basically says that as long as we have our sample space, that is omega, normalized to an area of 1, like we always should, that the probability of an event occurring within that area is just equal to the area. So to turn this into an example, let's say that we want to find the probability that my x plus my y is less than or equal to 1/2. So that's just a line down here, and we can say that this is the line x plus y equals 1/2. Now, while this may seem a little bit tricky to look at, remember that this is just a triangle, this area down here that has a x-intercept and a y-intercept of 1/2. So if we know the x and y-intercept, we now know the base and the height of our triangle, and we can recall from basic mathematics that the area of a triangle is just equal to 1/2 base times height, which in this case is just equal to 1/2 times 1/2 times 1/2, which is 1/8. So the probability in this case is just 1/8. Now, the next example is to find the probability of x and y where they're equal to 0.2 and 0.3 respectively, or of this set point. And as you may recall from a previous lecture, we kind of gave this one away already, but we'll rehash it. In a continuous space, the probability of being at a single point is just equal to 0. And in this case, if we go back and say the probability is equal to the area, we can also go back and say that the area of a single point, of any point, is just equal to 0. For any probability, the general steps that you'll want to go through when you're solving a probability, first is to specify the sample space. And that includes normalization if necessary to say that the area of your sample space or the total probability of your sample space is equal to 1. The next thing, and this gets a little bit arbitrary, is to specify your probability law. That is, what is the probability of each of those outcomes occurring within your probability space? The next part is to identify the event or events of interest. So if I have several different events out here, identifying which ones I actually care to find out if they are true, to find out what the probability is. And then the last step is to just crunch the numbers, to actually calculate the probability. And so being able to follow this very simple, honestly, 4-step process is behind every single probability problem that we'll discuss this semester. Being able to first correctly identify the sample space, then specify the laws or the probabilities of each of those potential outcomes, identifying what outcomes or events you're interested in, and then actually putting numbers to it and calculating that probability.